Oh, here we go. Thanks. So this is an introduction to Boskovic given by my friend over in Serbia, Professor Dragoslav Boscovich. And the plan is I'm going to go through this. It's about existential crisis, and then there's a video of some experts talking about Boscovich by way of introduction, and then it's Professor Stoiljkovich, and if there's time it will be Einstein, not Einstein, a few things about Einstein. Right. So basically, there's an existential crisis that was caused by Galileo that plunged which he plunged the church into, and which science and physics still suffers from now. This is Galileo, and poor Galileo, as we know, was persecuted by the Inquisition. But what is usually ignored is the church then tried to recover from the humiliation of silencing Galileo. So they managed to silence him. He went before the Inquisition. They told him to shut up about what he was talking about, and they put him under house arrest. So basically they won on a personal level against Galileo, but on a bigger level they shouldn't have won against him. So what the church then did was they put their top man on the case to try to sort out the mess from having won against Galileo, and this is their top man, who's Father Boscovich, who was from an area of the world which was once Yugoslavia. So I want to go to the first video by way of introduction of what some experts say about Boscovich.
Boscovich was born in the independent Republic of Ragusa, today Dubrovnik, on the Adriatic Sea. And together with another brother, he was educated by the Jesuits and became a Jesuit himself. Ragusa was an old republic, a republic that lasted for about 5 centuries, and was rigidly divided in 3 different classes: aristocratics, middle class, and lower class of workers. And the political power was in the hands of a very small aristocratic class. When Boscovich was 15, he moved from Ragusa, Dubrovnik to Rome, and kept being educated by the Jesuits, and studied and later became a professor at the Collegio Romano.
The Society of Jesus had a very important tradition in the physical-mathematical sciences, owing to the fact that mathematics had been included in the Society's teaching programs since the middle of the 16th century, while biological sciences and naturalistic disciplines in a larger sense of the word were forbidden by the Society constitutions. Loyola had explicitly forbidden to teach biological subjects because the canon law forbids clergy to exercise medicine. This was the root of this phenomenon. As for Boscovich, his position is partly strictly Jesuitical and partly original, in the sense that his training was entirely internal to the society tradition, but independently he was studying what was produced outside the society, mainly French science and Leibnizian science, and then also Newton. So that he mastered Newtonian physics very early, and when he, as a young man, became professor of mathematics in the Collegio Romano, he was able to introduce the more mathematized parts of Newtonian physics into his teaching. This was the beginning of his career, but also of his problems, because some basic assumptions of Newtonian physics were not only outside and against the Aristotelian principle, which were still taught by his colleagues in philosophy, but also against some basic tenets of the society's doctrine. Boscovich tried to conserve some of the basic tenets of the society within a new approach, a new doctrine, and this was his originality, but also the spring, the source of all the problems he met within the society.
This period is very interesting because up to the 50s, in particular up to 56, Boscovich elaborated his main ideas in the field of natural philosophy.
Boscovich created one original natural philosophy system who has a deep inspiration in Newton's natural philosophy. I think that Boscovich was a very profound reader of Newton, not only of Principia, but also of the queries of his optics. And it was very stimulating for him in an earlier period, before his study of theology, for example, when he studied the phenomenon of aurora borealis, but also in a period when he created his own natural philosophy system, because in earlier treatises, De Viribus Vivis, De Materia Divisibilitate, De Lumine, we have a choice of excellent quotation of Newton. And we have also the documentation how Boscovich developed from Newton's starting points new building, something what Boscovich called New World in his correspondence.
Yes, I think his main work, the Theoria, published first 1758 in Vienna and then in an extended version in Venice 4 years later. Basic law was such that it allowed a very large variety of combinations of these puncta, of these elementary particles. And this explains the huge variety of forms and properties of matter we find in nature, going from the smallest entity up to living organisms.
published in the middle of 18th century. There are several Latin editions during the Boscovich life. There are also 2 edition English version in the last century, and there is also one edition in Croatian and Latin language published. You can see that. What is the title of this theory? Theory of natural philosophy, reduced at one unique law of the forces that exist in the nature. See, one unique law, but many forces, not just one kind of forces, for all kinds of the forces. So, Boskovic believes that most simple elementary particles of matter are like points, very small without any dimension. But there are forces acting between these 2 points. If the one point is at position A and the second point is at position C, so they are apart, far away, there will be some attractive forces like Newton's gravitation. But if this point approach to this one, the forces attractive will be reduced, became 0, then repulsive forces will appear. Then again became 0, then attractive, repulsive, so several times, but finally, when this point comes to this position, close to this first one, there will be so strong repulsive forces that prevents those points to touch each other. But in any case, these 2 points will make one pair of points. And this pair of points is so-called, this is first order particles, means 2 points connected. These first order particles also can interact with each other. One first order and second first order. And again, we have, I always make mistake. So, again we have a situation that same law is valid in the second case. Again, first order particle will be, one will be here, second will be here, and then again we have the same story. And then these second order particles, are formed, and again the same law. And then atoms, molecules, and so on. So according to Boskovic, there is some hierarchy of matter. But whatever is the step in this hierarchy, whatever is the level, always this unique law of forces is valid. Although Boskovic emphasized that number of arches, their size and shape can be different. He drew also such type of the graph, with lower number of, or some of this type. Boskovic pay attention of those distances where the 0 is the force. Where the 0 is, force is 0. Where the force is 0. And there are 2 cases, so-called cohesion and non-cohesion limits. In the case of non-cohesion limits, what does it mean? If one particle is here, and second, for example, at a distance P, force is 0. But if from any reason distance is increased, repulsive force will appear and move it back far away. And contrary, if the distance decreases, attractive force will appear and pull it more close. So this is unstable position, this one, and this one, and this one. But contrary, cohesion limits. If one particle is here and second is here, this is stable position because if the distance increases, attractive force will appear and move it back. Or if the distance is decreased, repulsive force will appear and again move it back. So this is stable, so-called cohesion limit, stable position. This is also stable position, this one and this one. But also he explained that if this is in the center, the second one can be anywhere on the circle, the radius of which is AR, or in the circle radius of which this one, N. And he drew such orbitals, like this. And this is stable position of one point in the center, and the second one particle is in the center. A second particle is somewhere on this orbit, or this, or this. Also, he explained that the area delimited by the curve and abscissa represent any increase or decrease of the square velocity of the particles. What does it mean? If one particle is here, second is here, attractive force will bring close and accelerate it. Now repulsive force will decelerate it, reduce the speed, velocity. Then again velocity will be increased, and so on. And so the particle will change the velocity. And what it will be the change? So the square of delta V square is proportional to this area. This is not that good. This is according to Newton mechanics. So she just explained. And what should be noticed? This is definite value of energy. Because delta V multiplied with mass of the particle and divided by 2, this is energy. And this is definite quantity of energy, each this surface. This is, according to present terminology, quantum of energy. Boskovic didn't use this term in that time, but meaning is exactly what we call quantum of energy. And there are two cases. This is quantum of repulsive energy and quantum of attractive energy. Such quants of repulsive energy and attractive. And he also explained, if the surface area of this repulsive quantum of energies this has a lower value than this one, pink one, attractive, the particle will come up to the point E. And second, and first is here, and it will oscillate and going around it, but all the time oscillating like here, as he wrote in his book. Also he explained, if one particle is in the center, a second is somewhere on one of this orbit, and move from one to second orbit, it will lose a definite quantity of energy, or gain definite quantity of energy. So this is total quantum theory. So it is true that Boscovich theory is the very first quantum theory, and it is false what today physicists say, that Max Planck discovered quantum theory. It is not true. And furthermore, it is not true. At the end, during the 19th century, the chemical atoms were discovered, how to say, by Dalton and the others. People believed that those atoms cannot be divided. But at the end of 19th century, physicist John Thomson discovered there are electrons in atom, negatively charged electrons. And the rest of the atom is positively charged. And the open question was how those parts, negative electrons and the rest positive, how they are arranged in atom. Sorry, Thomson wrote in his book, and he did a lecture about that, about two models. One model is Planck-Padik model. It means whole atom is positively charged, but negative electrons are somehow distributed in this positively charged atom, like Planck in the Padik. This is one model. But also, there is another model he wrote in the same book. This is copy of this part of this book. And he wrote, suppose we regard the charge ion as Boskovic atom, and then he drew the Boskovic curve, put the orbitals where it should be, and say this is stable orbitals can be explained by Boskovic. So, but still the open question was, what model is correct? What is better? That was in this period. Ernest Rutherford was ex-student and ex-assistant of Joseph Thomson, and in this year he took a chair of physics in Manchester University. In this period, he performed well-known experiments with alpha particles or bodies of metal, and he concluded that planetary model is more correct. And because of that, this model was named Rutherford's model of atom. Just in that time, and he published his results, Niels Bohr from Denmark just finished his PhD on electronic properties of metal, and visiting 7 months he was with Thomson in Cambridge, and after that 3 months with Alfred in Manchester, just in that time, you can see. And what Niels Bohr done? He just calculated the forces, energies and orbitals and energies, and he took into account that this is quantum effects in these orbitals. So, one historical of science, Gilles, wrote in this book, Roger Boscovich, forerunner of modern physical theories. He wrote that it is more correct, this model atom to be named Boscovich Thomson model atom, because Thomson deducted his hypothesis directly from the theory of Boscovich and showed that the notion of allowed and forbidden orbitals follows from this Boscovich theory, and Boscovich laid the foundations of the theory developed later by Bohr and others. Where Boscovich planted 200 years ago, others have made. So it is well known in literature, nothing new. For me, what was important? There are people dealing with Boscovich, not so much, but very well known physicists in our country, in Croatia, and worldwide, dealing with Boscovich theory and presented it. But what is strange? Nobody, absolutely nobody asked himself, is this theory correct or not? Considering this model of atom, it is correct. But what is important? Boscovich emphasized that his unique law of forces is valid for at any level in the structure of matter. And nobody asked himself, and nobody checked it. I did that. So, because if the Boscovich curve is correct for any level of structural matter, this is one stone. If it is not correct, we can speak about Boscovich as a man in the history of science and so on. So let's see what is the empirical data. This is atom chemical interaction, presented in this book quite recently. And it explained that two atoms, when they chemically react, the potential energy is changed with distance. And there are stable positions at minimum potential energy and minimum potential energy. But it is well known that force is just derivation of energy with distance. So this is Boskovich's curve, this is modern science curve. Minimum potential energy means zero force. Zero force. Stable position is cohesion limits according to Boscovich, and minimum potential. This is the same. Those curves are interconnected. If you know one, you can derive the another one. So concerning atom chemical interaction, it can be said that this is just one of the type of Boscovich curve I presented before. But two atoms can interact not only chemically, can interact physically. And the question is, what is the physical interaction between two atoms? How to explain it? We can ask Boscovich. And he answered, by my unique law of the forces. Let's check. Here is atom-atom physical interactions. There are a lot of examples. I gave only two. This is typical Boscovich curve. Two atoms, if it is combined, if they are combined, they produce molecules. So we can ask, what is the interaction between two molecules? So we are at high level. First was nucleus, electron. Now atom, atom. Now we are going to higher level, molecule, molecule interactions. The same answer gave Boscovich. And there are examples. This is also one type of Boscovich curve. those molecules can be chemically combined, producing macromolecules. And it is generally believed, accepted, that macromolecular hypothesis was presented for the first time by Hermann Staudinger in 1920. Is it so? Boskovic wrote that atoms could be connected in a very long series by cohesion of the parts of the atom, and they will have spiral shape and elastic properties. So this is macromolecular, long series of atoms. This is macromolecular. And indeed, some natural, as well some synthetic polymers, have spiral shape and elastic properties. Of course, we can ask ourselves, what is the interaction between two macromolecules? How to explain it? Of course, we should ask Boskovic. His force. That's right. Indeed, it is like this. Boskovic has a right. At higher level above macromolecules is colloidal part. Sorry. Boskovic proposed also that continuous series of little cubes can be formed. This is a nanoparticle. We know that nanoparticles exist. Maybe not this shape, but they exist. Of course, we can ask ourselves, what is the interaction between two nanoparticles? Shall we ask Boskovic? Okay. By my unique law of forces, don't ask me again. Let him to be in rest. I will not ask him again. Because the interaction between nanoparticles is explained with Boscovic's curve. This is quite new result. Up to now, okay, there is colloidal particles. It is a higher level in structure of matter. Also Boscovic's curve. So up to now, I give to you examples from one level, second, third, fourth, sixth level. Now we shall go deep in the structure, deep in inside the atoms. Parts of nucleus and heavy atoms, nucleus and lambda zero hyperions, nucleus only, neutrino and quarks. I will go to save the time, just present like this, and you see there is examples. There are a lot of them. Leon Liederman.
The introduction to the Dragoslav's talk. So, what the church has done is they've built science on Aristotle, and Aristotle is the father of logic. And Galileo had thrown all that into chaos with his observations. So he got some of the priests and that looking through the telescope. But the church had tried to dominate science, and they had started to learn the importance of observations, but they built their logic on the observation of things like sunrise and sunset. So you observe that, and you think to yourself, well, the Earth isn't moving, and it's the sun moving. So they had built to a large extent on observations. And of course, when you're looking at read Aristotle, you think, well, some of the so-say observations he made were incorrect. But basically, one of the fundamental observations is, well, it looks like the Earth isn't moving, and it's the sun that's moving. So if you can build up a logic system of science based upon that observation, then you are quite happy. But Galileo brought that observation into doubt by trying to provide evidence that the Earth moved around the sun, and it's really more accurately they're moving around a common centre of gravity. So what you're faced with is, if you could not rely on the observation that the sun moved around the Earth, what observations could you rely on? And answer was, you couldn't rely on anything. Reality we perceive is different to what our senses of sight, sound, touch, etc. tell us. So you've got this fundamental problem if you can't rely on that observation of what your senses are telling you, you can't rely then on anything your senses are telling you. So back came the idea of atoms, and atoms goes a long way back to Democritus, and based upon normal observations in daily life, nobody's seeing any atoms. So it's not really a theory based upon observation which you could make back in those times. And so when they're looking at a theory which could be based on atoms, what type of atoms did they decide upon? And the answer was they decided that the atom was a point particle. And this is meaning atom in the context of a particle you couldn't split to something smaller. When you've got a point in maths, you can't, so to say, split that any further down. So you're identifying the smallest particle in physics as a point particle. So really, modern physics is based upon the idea of point particles, and it goes against our feelings of common sense, so therefore it becomes an existential crisis. So presumably one of the reasons it is omitted from most physics courses, i.e. teaching about the theory of point particles, is because the human way to cope with an existential crisis is to ignore it and pretend you don't have one. So from my observations of people, when they've got a problem, often if it's too big and they can't think of any way around that problem, they try to skip over it and carry on in their thinking process. And sort of like physics is sort of like the same thing. When they're teaching physics to people, they're sort of like, if there's a problem with something, they don't want to go into too much details about it, so skip over it. And this is the same thing with this point particle theory. They talk about point particles when you've been taught physics, but they don't go into the details of what the theory is behind the point particles, because it would cause problems. So skip over that. And they skip over that, and any other problem they come along which is too deep, they try to skip over that as well. So this is the education system and the way people kind of cope with things which they can't deal with. So at the fundamental level of the Copernican Revolution, it led to this bringing back the theory of atoms, and the theory which modern science decided to base itself upon was this existential crisis. You try to think about point particles. If you think about it too much, it doesn't really make sense because it's not conforming to your senses. When they start talking about things, this table and so forth, made of particles, and most of it's empty space. 99.99% of it is not there. And that does not correspond to what your senses are telling you. But you're supposed to look at it in closer and closer detail with things like electron microscopes, and you see beyond your senses. So, the father of modern atomic physics was this person. It's Father Boscovich. And I would have gone into that video, and that was sort of my introduction to the video of Dragoslav. You've got this idea of point particles, and when you develop that theory further, you are led into all sorts of problems. And so I think if you were teaching to physics students how physics really progressed from Galileo casting doubt upon the existing observations that they had at that time, and trying to show that physical reality was different to what your senses were telling you, and you were coming up with a theory which to most people doesn't make sense, and that is an existential crisis. And they've just built upon it further and further and further. So the next one is Einstein. I've got time for him. So on to Einstein. I've tried to make sense of Einstein, and one of the big fundamental problems with Einstein is he doesn't provide any references. So when you're reading Einstein, you cannot find the context of what he's talking about. He's going into physics, but in the history of physics, what is the connection to what other people have said before him? It would be nice to have a few references to say what is his line of thought. So, one of the big problems I found is that there's a conflict between Newton and Leibniz. And when I look at Einstein, I find maybe he was going more along the lines of Leibniz than Newton. So I feel that it is a misrepresentation of Newtonian physics most of the time by Einstein. And I would have gone into more detail about that, but I think I should finish it there. Otherwise, thank you.
Are there any questions, assuming Boscovich was ahead of his time? Are there any of Boskovich's works or principles that the physics community has not caught up with yet? Is there anything left out that we've still haven't done that is predicted?
Well, I'm trying to make a coherent sequence of progression of ideas, and there isn't one. There's sort of like, the faith is, as I said, an existential crisis straight after the Copernician Revolution. It was an existential crisis, and it didn't make sense, and so you skip over that problem, and you go on to the next one, and you've got a problem, skip over, go into too much details about that, and you go on to the next one. So there's no progression of physics development, which makes proper coherent sense.
But should physics make proper coherent sense? One has a belief, you go up to that, and somebody comes along and says, "Oh, this is BS."
Bullshit, yeah.
Yeah. I was just trying to be polite.
Sorry.
And a new theory gets there. So it is a step uncoherent towards the development of a physical reality or mathematical description of reality.
It seems to be building upon things which don't make sense, and you keep building upon it. And so you've got one theory which doesn't properly make sense, and go forward a bit and add a bit more to it.
No, but that is contradictory what you said before. What I understood what you said before was you go along, the thing that doesn't make sense, you discard it all and start with a new theory. That's what you said before. Now what you're saying was, which is what basically we all try and do. We build up the theory. Okay, now it's, modern physics is building on foundations that have been laid up to, in the 1900s to 1950. Those are the foundations that everything is built on. But before that, what I understood what you said was that something was there, but thrown overboard and something new started.
The big fundamental one was with Galileo.
Yeah, correct. But that is physics. If somebody comes today and brings forward a theory that just the whole thing could fall and we'll start on a new theory. The physics today as we understand it could tomorrow or the day after tomorrow fall completely and we build up a completely new mathematical model. If the
I would say the fundamental within modern physics as to what they're building upon is this idea of point particles, and it's very difficult to discard that idea. If you're talking about a theory which is going to discard that, then it's really something that's used a great deal. So there's kind of restrictions on what you're allowed to discard, so you can add to it and come up,
First, thanks very much for the presentation.
Okay.
Stuff. You gave both the background in the authority system behind it and the content in the sense of this ripple of force that seems to be so universal there. I just would like to add the remark that if anyone who's not been aware of it, my approach to the particle, the infinitesimal particle thing, and the problem of force are both addressed, and doing the simplest model I can that doesn't allow those, produces eigenfunctions with radial ripple is although they're not a force function, they do confine the electron in these bands of radius. Okay? So that it sort of fits with the
point particle theory.
Boskovich's, yes, except we don't need a point particle. Because all I'm saying is we don't like the point particle because it offends us with the infinities.
Yeah.
And we also need something to deal with its geometry around the atom. And with what is the simplest wave process I can put together as being fundamental, it produces that. And it's believed not to.
Yeah. But with, as I say, Dragonslaw, when you develop the point particle theory, it does get more complicated. And it does evolve to quantum physics.
Okay,
but if you're going to address the issue, we want something to replace point particle theory. Well, one of the biggest problems is it's not taught. They've omitted it, they jumped over it. So you've got physics people.
It's like you were saying,
so
people haven't seen how you might go about or not showed sufficient push to deal with that problem.
So something like Wittgenstein said, what we don't talk about, we move over in silence. So the point particle theory, they don't talk about it.
Right.
So nobody's discussing the issue of should we have this point
so
particle.
my claim is that I have faced it.
So they're just avoiding teaching it, so nobody's talking about any problems with it.
Indeed, I think your picture was terrific.
Yeah.
Okay, can I suggest that Roger kindly stop this talk early. Let's get back on track.
Okay.
And